the next part we have to study is the work done in an adiabatic expansion. Adiabatic expansion, we have to derive the equation for work done in an adiabatic expansion. So we know the adiabatic process in some simple. First, I told you in some first few lectures that basic terms used in the thermodynamics. So adiabatic process, I told you. What is adiabatic process? There is no heat enter the system or no heat evolve from the system. No heat enter the system or no heat evolve from the system. Such process is known as adiabatic process. And here adiabatic process means Q is equal to 0. Q is equal to 0 for adiabatic process. Now look here from first law of thermodynamics. What is statement? Q is equal to delta E plus W. Delta E plus W is the mathematical statement of the first law of thermodynamics. So in case of adiabatic process, what is Q is equal to 0. So the equation becomes 0 equal to delta E plus W. What is if you rearrange for delta E equal to this W becomes minus N. Delta E is equal to minus W. Or in case of PV type of work, pressure volume type of work, how can we write pressure volume type of work? We can write in this way: delta E is equal to minus P delta V. Delta E is equal to minus P delta V for infinitesimally small quantities. Infinitesimally small changes. For infinitesimal changes, we can write this equation. We write in this form: dE equal to minus P into dV. dE is equal to minus P dV. So we obtain this equation. Now here we know that ideal gas equation, PV is equal to RT for 1 mole of gas. So P is equal to RT upon V from ideal gas equation. You know PV is equal to RT for 1 mole of ideal gas. So P equal to RT upon V. So substituting this value here. So dE equal to minus value of P here RT dV upon V. RT upon V means here RT dV upon V. Now from the definition of heat capacity at constant volume. What is heat capacity at constant volume? CV. CV equal to dE by dt. dE by dt for heat capacity at constant volume. So here heat capacity at constant volume CV equal to dE by dt. And what is value of dE then? dE equal to CV into dt. This dt gets here. So here we can write CV dt. So if dt is taken here, then CV dt equal to dE. So we replace dE by CV dt. So CV dt equal to minus RT dV upon V. Now this T we have taken to the left side here. So we can write CV dt upon T equal to minus R dV upon V. dV upon V. By integrating this equation, between limits T1 to T2 for temperature and volume V1 to V2, we can write directly integral here. CV log of dt upon T, integral is log of T2 upon T1 equal to minus R log of here V2 upon V1 for V2 upon V1 here. Now we can write CV log of T2 upon T1. If we take reciprocal of this V2 upon V1, if we take V1 upon V2, then this minus sign removed from here. So R log of V1 upon V2. Okay. Now Again, rearranging this equation, log of T2 upon T1 equal to CV taken here. So R upon CV log of V1 upon V2. Log of V1 upon V2. Now, here we know that one famous equation for heat capacity at constant pressure and heat capacity at constant volume. What is that equation? That is Cp minus Cv equal to R. That is the equation. Cp minus Cv equal to R. Relation between gas constant, heat capacity at constant pressure and heat capacity at constant volume. So the equation, so replacing this term R here, we get log of T2 upon T1 equal to Cp minus Cv upon Cv into log of V1 upon V2. Okay, separating the variables here, we can write log of T2 upon T1 equal to Cp upon Cv minus Cv upon Cv log of V1 upon V2. Okay, so if we are replacing this term, that is Cp upon Cv by gamma, Cp upon Cv by gamma. So we can write log of T2 upon T1 equal to, replacing this term gamma, minus here Cv upon Cv 1, gamma minus 1 log of V1 upon V2. If you write this equation in the logarithmic form, we get T2 upon T1 equal to V1 upon V2 raised to gamma minus 1. So logarithmic form is here gamma minus 1. Okay, and in more rearranged form we can write this equation. If T1 is here, then we can write T1 V1 raised to gamma minus 1 equal to T2 V2 raised to gamma minus 1. If more than two component system, we can write T3 V3 equal to gamma minus 1, and we can write so on. Okay, so if from the equation, ideal gas equation, that T1 V1 equal to R T1. So replacing the value of T1 here, T1, similarly replacing value of P2 V2 equal to T2, replacing the value of T2 T3. So similar way we can write this equation in the form. I am writing here. We can write this equation in the form. Here P1 V1 raised to gamma equal to P2 V2 raised to gamma equal to P3 V3 raised to gamma, and so on. So in general we can write PV raised to gamma equal to constant, and this gives the work done. This equation gives work done in adiabatic expansion. This gives work done in adiabatic expansion. Okay, so I am repeating once again. We are deriving the equation for work done in adiabatic expansion. So work done in adiabatic expansion here. Adiabatic means the process in which no heat evolved or absorbed by the system. So if no heat enters the system, leaves the system, heat content remains 0. Q is equal to 0. So Q is equal to 0 here. Then from first law of thermodynamics, mathematical expression of first law of thermodynamics, we can write Q is equal to delta E plus W. But for adiabatic process, Q is equal to 0. So 0 equal to delta E plus W. So delta E is equal to minus W. If you rearrange this, delta is equal to minus W. Now for pressure volume type of work, we can write W is equal to P delta V. So we written this equation, delta E is equal to minus P delta V. So in very small quantity, very infinitesimal form or differential form, we can write dE for delta E equal to minus P dV for delta V. So dE is equal to minus P dV. So this equation we obtained here. now at this stage, from ideal gas equation we substitute the value of P here. Okay, P RT upon V. So we substitute this value of P here, RT upon V. Substitute value of P here, RT upon V. Now at this stage, again value of D is here from heat capacity at constant volume. So heat capacity at constant volume, we can write CV equal to D upon dt. So CV dt equal to D. So value of D obtained from this equation, we put this value here, CV dt equal to minus RT dV upon V. Now at this stage, rearranging this equation, we have taken integral of this equation between limits T1 and T2, V1 and V2. So we get integral here. This is integral, rearranging this equation, and again substituting value of R, the famous equation Cp minus Cv. So substituting value of R here, we get this equation, and at this stage we again rearrange this equation, and separating the variables here, we obtain Cp upon Cv minus Cv upon Cv log of V1 upon V2, where we assume gamma for the term Cp upon Cv. So we replace this Cp upon Cv by gamma minus Cv upon Cv1. So we obtain this equation, and this equation, if we written in, we have written it in differential form. So we get this equation from ideal gas equations. We can write this equation in the form P1 V1 raised to gamma. Here substituting the value of T1 T2 from all these equations, we can write P1 V1 raised to gamma equal to P2 V2 raised to gamma, P3 V3 raised to gamma. So in general we can write PV raised to gamma equal to constant, and this is the equation for work done in adiabatic expansion. Okay, so the next point we have to study is the concept of entropy. The important concept in thermodynamics, concept of entropy. So entropy, in simple words we can say that entropy is the measure of randomness or disorderness in the system. Measure of randomness or disorderness in the system. So we can write here entropy. Entropy is indicated by symbol S. It is the measure of randomness in the system. Measure of randomness, we say chaos, disorderness in the system. Disorderness, more disorder, more entropy in the system. Less disorder, less entropy in the system. So famous example for this is conversion of solid to liquid and liquid to gas. As we know that the molecules in the solid are more arranged due to the higher force of attraction. Intramolecular force of attraction is higher in solid, so more arranged structures is there, more arranged ions, molecules, atoms, etc. So these are in more arranged state. So arranged state means low entropy. Entropy of the system is low. If we see the structure of liquid, then liquid, the force of attraction decreases and liquid molecules are more free to move, and that's why the order in the liquid decreases. So disorderness increases, order decreases, disorderness in the system increases, and that's why entropy goes on increasing from solid to liquid. And if we see the gaseous molecules are more, the forces are very negligible in gaseous molecules, so they are very free to move than the liquid, than the solid. So the randomness or disorderness in the gaseous molecules is more as compared to the liquid and solid, and that's why if we know that more randomness, more disorderness, more chaos in the system, then that system is with the great entropy or greater entropy. So here entropy again increases from solid to liquid to gas here. So entropy increases in the sequence as the disorderness of the system increases or randomness of the system increases in general, the exact absolute value of entropy is difficult to find out. Exact value of entropy, yes, but we can find the change, which is the heat provided Q reversible upon T. So the equation to find out the change, entropy change, delta S is equal to Q reversible upon T. So this is the entropy where we can find the disorderness of the system increases. Disorderness in the system increases, then entropy of the system increases. So next point that we have to study is the entropy change in the irreversible processes. Entropy change in the irreversible processes. So for entropy change in irreversible process, we have to see entropy change for irreversible process. Irreversible processes. Entropy change for irreversible processes. Now for irreversible processes, consider irreversible cycle here. Consider here irreversible cycle. Irreversible cycle. So irreversible cycle, suppose that Q2 is the amount of heat absorbed for your irreversible cycle. Q2 is the amount of heat absorbed at temperature T2, amount of heat absorbed at temperature T2, and Q1 is the amount of heat absorbed at temperature T1, amount of heat absorbed at temperature T1. So from Carnot cycle is the important part of thermodynamics. So Carnot cycle, we can define efficiency. Eta is the efficiency term. So efficiency defined by Q2 minus Q1 upon Q2. In the similar way, in terms of temperature, we can define efficiency T2 minus T1 upon T2. So if we consider here for reversible process, reversible engine works in temperature with same temperature range, T1 and T2. Reversible engine works between the same two temperatures T1 and T2. Then we can write for reversible process Q2 minus Q1 upon Q2 is less than T2 minus T1 upon T2. For reversible process, this is the Carnot cycle efficiency. We can write Q2 minus Q1 upon Q2 is less than T2 minus T1 upon T2. Or we can write this equation in another form. Same equation, but we can write in another form. That form is the 1 minus Q1 upon Q2 is 1 minus less than 1 minus T1 upon T2. 1 minus T1 upon T2. So here another form, we can write this equation in another form also. If this quantity is greater, Q1 upon Q2 is greater, then this is possible. Because if we minimize this quantity from 1, then it should be less than the T1 upon T2. So for this purpose, this quantity must be major. So in order to obtain this equation, so Q1 upon Q2 is greater than T1 upon T2, then this is possible. Okay, if this quantity is larger, then this value is lower. Okay, this quantity Q1 upon Q2 is larger than T1 upon T2, then 1 minus Q1 upon Q2 is greater. Okay, so this equation is here. Now in this case, Q1 upon Q2 is greater than T1 upon T2. So we can write in another form also. Q1 upon T1 is greater than Q2 upon T2. Q1 upon T1 is greater than Q2 upon T2. So from the definition of entropy, look here. From